So let's talk about a concept that's really changing the game in data security. It's called homomorphic encryption. And at its core, it solves one of the oldest problems we've had in computing, the fact that you've always had to trust the machine that's handling your most sensitive information. For years, this was the kind of thing you'd only hear about in cryptography papers. It was almost like the holy grail, theoretically possible, but just not practical. Well, that's not true anymore. Homomorphic encryption isn't some academic prediction, it's here. Engineering teams are deploying it right now to solve real-world problems.
To really get why this is such a big deal, you have to ask, where's the weak link in our data security chain? You know, we've gotten really good at locking down data in a couple of key states, but there's this one critical moment where almost every system we've built is, by design, left wide open.
Okay, let's break that down. We use strong encryption to protect data at rest. You know, when it's just sitting on a server's hard drive. And we do the same for data in transit while it's zipping across the internet. But what happens when you need to actually do something with that data? You have to decrypt it. And in that moment, when it's being processed, your sensitive information is just sitting there in what we call plain text. It's completely exposed. This means you have to place total trust in the server that's doing the work.
This is exactly where homomorphic encryption flips the script. It completely breaks that requirement of trust. See, it's a special kind of encryption that lets you perform operations directly on the encrypted data, the ciphertext, without ever having to decrypt it first. The best analogy is to think of your data being locked inside a transparent, unbreakable box. You can reach in with special gloves and manipulate what's inside, but you can never actually see or touch the contents directly.
So here's how that flow looks in the real world. First, you encrypt your sensitive data right on your own device, before it goes anywhere. Second, you send that locked-up data to a cloud service. They can then run their computations, analytics, machine learning, whatever, directly on your encrypted data. And finally, they send the encrypted result back to you. You, and only you, have the key to unlock the final answer. The cloud provider, they learn absolutely nothing. Not about your input data, and not even about the outcome.
Now, this isn't just some theoretical security upgrade. This actually unlocks completely new ways for businesses to work together and innovate, all while maintaining the absolute highest standards for privacy. Let's look at a couple of use cases.
Okay, picture a company that wants to analyze customer data to make their product better. With homomorphic encryption, they can collect user data that's been encrypted on the user's own phone or computer. Then they can run these massive, large-scale analytics in the cloud to spot trends. The company gets the valuable insights it needs, but it never, ever sees any single individual's personal information. And this is a huge one for AI. A hospital, for example, could use a cutting-edge diagnostic AI model from a third-party company. They could send encrypted patient scans to the service, get back an encrypted diagnosis, and then decrypt it safely behind their own firewall. Patient privacy is perfectly preserved, and the AI company's valuable proprietary model is also protected. It allows for collaboration without exposure on either side.
This technology is also an incredible tool for dealing with all the complex privacy laws out there, like GDPR or HIPAA. By using homomorphic encryption, an organization can literally give a mathematical guarantee that a third-party processor never has access to raw personal data. It makes compliance checks and audits so much simpler.
Now, I have to put my engineer hat on for a second. This kind of power doesn't come for free. There are some very real, very practical trade-offs that we have to manage when we build these systems today. Right now, the two big hurdles are performance and complexity. First, doing math on encrypted data is just slower. It's a lot more computationally intensive than working with plain text. Second, it's more complex for developers. You can't just use your standard programming libraries. You have to think differently and structure your code to work within the mathematical limits of the encryption. These aren't deal breakers, but they are serious engineering challenges you have to account for.
The good news is, the industry is moving incredibly fast to solve these issues. We're starting to see specialized hardware, things like ASICs and FPGAs, that are built specifically to accelerate these kinds of computations. And at the same time, the software libraries are getting way more advanced and much easier for developers to pick up. So that gap in performance and complexity, it's closing, and it's closing fast.
Which brings us right back to the fundamental idea here. This is the core value proposition. For the first time in the history of computing, we can separate the act of computation from the requirement of trust. We can tap into the massive power of the cloud without having to blindly hand over our most sensitive data.
So I want to leave you with this question.
As this technology gets faster, cheaper, and easier to use, what new things become possible? What kind of problems could you solve? What services could you build if that barrier of trust was just completely gone? The possibilities are really profound, and honestly, we're just getting started.